Hi everyone, in this video I'm continuing to work through question 11 part C of the 2020 Extension 1 trial exam from James Ruse. So it's a 3-part question and I've already worked through part 1 in a prior video, so take a look at that if you haven't already. And in this video I'm going to focus on part 2, which says hence find, without the use of calculus, the coordinates of the turning points of the curve y is equal to 2 divided by 3 cos theta plus 4 sin theta in the interval 0 to 2 pi inclusive. And the word hence at the beginning of this part gives a very strong indication that the work we just did in part 1 is going to become very useful, so it's worth trying to see the linkages there. And hopefully it's quite clear to see that in part 1 we've found an expression for 3 cos theta plus 4 sin theta. And then here in part 2, the equation or the curve that we're trying to find the turning points of has that expression in the denominator. So the link is hopefully quite clear to see. So yeah, let's take a look. So here's the basic requirements of the question. We're looking for turning points. Here's our equation. And we've got our domain of between 0 and 2 pi. And we're expressly told not to use calculus. But as I mentioned, the first, I think, natural thing to do is to draw the link between this denominator here and the expression that we just worked out for part 1. So we can actually write this curve as being equal to 2 divided by our 5 cos theta minus inverse cos of 3 on 5, which is alpha. And maybe just for simplicity in terms of writing, I might just leave alpha as alpha rather than writing it out, and we can just evaluate it when we need to at the end when it comes time to get out our calculator. So what I'll do, so in the denominator we'll just write 5 cos theta minus alpha, noting alpha is just our constant. And at this point, given we're told not to use calculus, we're not going to be doing any differentiating and working out when, first derivatives are 0 and all that kind of thing. I think the key to thinking about the turning points for this curve is to really hone in on the fact it's 2 on 5 as a constant multiplied by 1 over the cos curve. And even though it's the inversion of the cos curve, what we know about the cos curve in general is that it's kind of fluctuating and it's got a periodicity to it, and it's always turning around when it hits 1 and negative 1. And so actually we know the turning points of cos. We know it's the angles that get it to 1 and negative 1. And so the turning points of 1 over cos are going to be at those same angles. Whilst the actual curve is different, the turning points won't be different. So I think that's the key. I think what we can do is we can note that the curve, so y, will have turning points when our cosine curve, which is cos of theta minus alpha, has turning points. I think that's the essence of this question. And we know that cos theta minus alpha has turning points essentially at two key angles, which are all the angles when cos of theta minus alpha is equal to 1. That's all the maximum turning points. And then similarly when it's equal to negative 1. But what I might do is I'll work through this case when cos theta minus alpha is equal to 1, and then we'll work through negative 1. So hopefully if you know your cos curve, the angle that gives a cosine of 1 would be, in our case, theta minus alpha, which is our angle. That's going to be when it's 0, since we know the cos of 0 is 1. And then we go through the full periodicity of the curve to get back to 1. So it would be 2 pi, and then it would be 4 pi, and you keep going. So really, given we're concerned with theta, we need to bring this alpha over. So we'll have theta is equal to alpha, 2 pi plus alpha, 4 pi plus alpha, and so on. And at this point, it's worth noting that we have been given a very specific domain here between 0 and 2 pi. So all of these thetas that are outside that domain we can ignore. And so we've got alpha here, but beyond that, we've got 2 pi plus alpha. So we know that must be beyond 2 pi. And obviously 4 pi plus alpha is beyond. So all of these results we can effectively ignore. So really, in terms of this turning point, when the cosine of our angle is 1 at that maximum turning point, that happens when theta is simply equal to alpha. So we know alpha, we worked it out in part 1. So what we want to do is work out what the y value would be of our curve, because remember our curve isn't cos theta minus alpha, our curve is actually 2 on 5 cos theta minus alpha. We've made use of the fact that the turning points of this simpler curve will be the same, but the y value still, we need to do the work. Y will be equal, when we put theta is alpha, we get 2 on 5 cos, well, theta being alpha would be alpha minus alpha. So that would be, well, we know cos of 0 is 1, so it'll just be 2 on 5 times 1, or just 2 on 5. So therefore, we know we've got a turning point at the coordinates alpha, which back in part 1 we worked out in all of these formats. So I might just write it in decimal form. So 0.927 in terms of, that's a kind of probably enough precision for the purposes of this question. So 0.927 as the theta value, and then 2 on 5 as the y value. Panic boom! So that's one turning point, but as I mentioned, we also want to think about the case when cos of theta minus alpha is equal to -1, because the curve also turns around at all those points. So we know that happens when theta minus alpha is equal to, first of all, when we get to pi, that's when we're halfway through the curve and it turns around. And then using the periodicity, we just keep getting all the instances of moving 2 pi from there. So we get pi plus 2 pi, so we'll get 3 pi and 5 pi and so on. But just like before, anything outside of our domain we can ignore. So really we know we're ignoring all of this because it's definitely beyond 2 pi. So really we've once again just got one point that we're concerned with, and that would be theta is equal to pi plus alpha, bringing the alpha over. So again, in terms of what's the value of our curve, what's y? Well, that would be 2 on 5 cos, and for theta we're going to put pi plus alpha, and then we've got minus alpha. So this alpha minus alpha will cancel to nothing. So it's really 2 on 5 times cos of pi, and we know cos of pi is -1, so this just ends up being -2 on 5. So therefore we can conclude that we also have a turning point at pi plus alpha. So if I just get my calculator, if you've seen my video for part 1, you'll know I stored the value for our alpha. So if I add pi to that, we get that as 4.069 if I just stick with 3 decimal places. So 4.069 and then -2 on 5 as the y value. And I think that's it for that question. I think we've kind of made use of what we know about the cos curve to think about the turning points of this more complex curve, which actually is a relatively simple form of an even more complex curve that the question was actually about. So we've used what we knew about part 1, the result we showed in part 1, to get a relatively simple curve that we can make this key inference about, which is that the turning points, the values of theta at which the turning points will occur are the same. And so we use what we know about the cosine curve to specifically within our domain pinpoint the value of theta for when the curve will turn around. So we end up with these two turning points, and hopefully that's all made sense. I guess I could maybe hazard a guess that a lot of students might pick up one of these turning points, but maybe not both of them. I guess that could be a common error that could be made, or perhaps plenty of students might not just make the link, and whilst calculus might be the go-to technique for them, when you're specifically told that you can't use calculus, suddenly you need to get a little bit more creative with the approach that you're going to use. So hopefully now that you've seen that, it's something you could add to your repertoire and make use of it whenever you need to. So yeah, what I'll do in the next video is I'll work through part 3 of this question. All right, tick boom.